Have you ever wondered how your favorite song travels from a radio station miles away, right into your car? Or, how a text message just zips across the city to your friend's phone in an instant? Well, today, we're going to pull back the curtain on the invisible signals that pretty much power our entire modern world.
Okay, so let's just dive right into the big question. How do these invisible signals actually fly through the air to bring us everything from music and phone calls to all the data on our phones? I mean, it really does seem like magic, but it's all down to some truly fascinating physics. And that's what we're going to unravel right now.
All right, so the hero of our story is what's called the electromagnetic wave. Now, when we use these waves to carry information, we just call them radio waves. At their core, they are self-propagating packages of energy, and they travel through space at the incredible speed of light, which is about 300 million meters per second, just unbelievably fast.
So, how do these waves actually move? Well, they're made of two interconnected parts. You've got an electric field and a magnetic field, and they're oscillating at right angles to each other and to the direction they're traveling. It's this constant dance, a changing magnetic field creating an electric one, which then creates a new magnetic one that just keeps pushing the wave through space, even through a perfect vacuum where there's nothing. Okay, so if we want to build systems that use these waves, we obviously need a way to describe them, to tell them apart. And it turns out, every single radio signal can be defined by just 4 core traits. You can think of these as the fundamental building blocks for understanding all of wireless communication.
First up is wavelength. You'll often see it represented by the Greek letter lambda, and this one is super straightforward. It's just the physical distance the wave covers in one complete cycle. The easiest way to picture it, it's literally the distance from the peak, or the crest, of one wave to the peak of the very next one. Simple as that.
Next, we've got frequency, which we measure in hertz. Now, if wavelength is all about distance, frequency is all about time. It's how many complete wave cycles pass by a single point in just 1 second. And here's the crucial thing to get. Frequency and wavelength are totally inversely related. A higher frequency means more waves are packed in, so you get a shorter wavelength. A lower frequency means a longer wavelength. This is actually the basis for things like FM radio. That's frequency modulation, where we encode information by changing the wave's frequency.
Our third trait is amplitude. And really, this is just a measure of the wave's strength, or its power. A fantastic way to think about it is like the volume knob on your stereo. A wave with a higher amplitude is a louder, more intense signal. And yep, you guessed it, if you've ever heard of AM radio, this is the A. It stands for amplitude modulation, where the sound is encoded by varying the wave's strength.
And this is exactly why amplitude is so important. A louder wave, like the one you see on top here, has the strength to travel way farther before it gets drowned out by all the other random electromagnetic noise in our environment. I mean, the weaker signal might still be there at a distance, but it's basically undetectable. So it's simple. More amplitude means a longer, useful range for our signal.
And finally, our fourth trait is phase. Now, this one's a little different, because it's not about a single wave all by itself. Phase is all about timing. It's a comparison between 2 or more waves as they arrive at the same destination, like your receiving antenna.
And the effective phase can be absolutely dramatic. Check this out. On the left, when 2 waves arrive in phase, meaning their peaks and troughs line up perfectly, they actually add together, and you get a much stronger, much more robust signal. But look at the right. If they arrive out of phase, where the peak of one wave meets the trough of the other, they can completely cancel each other out, and you're left with basically nothing. This is exactly why sometimes just moving your phone a few inches can take you from 1 bar to full reception.
Okay, so we've got the basic properties down. But let's be real. In the real world, radio waves do not travel in a perfect, straight line through empty space. No way. They interact with everything around them. They bounce, they bend, and they get absorbed. So let's take a look at the signal's wild journey.
First up is reflection, and it's pretty much exactly what it sounds like. Just like a beam of light bouncing off a mirror, radio waves will bounce off of smooth surfaces. The catch here is that the surface has to be big compared to the signal's wavelength, so we're talking about things like big metal roofs, the sides of buildings, or even the ground itself. Then you've got refraction. This is what happens when a signal passes from one type of material into another that has a different density. When that happens, it actually changes speed and bends. I mean, if you wear glasses, you're using this very principle to bend light. For radio waves, this often happens because of changes in the atmosphere, like temperature or humidity, which can totally alter a signal's path over long distances.
Now this one is really cool, diffraction.
This is how a signal can literally bend around an obstacle. This picture shows what's called the knife edge effect. You see the signal hitting a sharp edge, like a mountain ridge or the corner of a building, and the waves actually spread out, filling in that shadow area behind it. This is a huge reason why you can sometimes get a signal even when you don't have a clear line of sight to the transmitter.
And finally, we have absorption. You see, when a radio wave passes through a material, some of its energy gets converted into a tiny amount of heat, and that weakens the signal. This is the #1 reason your Wi-Fi signal gets weaker as you walk into another room. The walls are literally absorbing the signal's energy.
And you can see right here just how different materials affect a signal. I mean, a simple window or some drywall might only cause a small drop in strength, which we measure in decibels, or dB. But just look at a concrete wall or a metal door. They can absorb a huge chunk of the signal. And that's exactly why getting good cell service in a basement or an elevator can be so tough.
So we've got these waves with all these specific traits, and they're bouncing, bending, and getting absorbed all over the place. So how in the world do we actually harness all this physics to build reliable communication systems? Well, this is where some really clever engineering comes into play.
I absolutely love this quote from our source material because it's the perfect way to understand how an antenna works. See, antennas don't create new power. They provide what's called passive gain by focusing the energy that's already there in a specific direction. It's just like cupping your hands to make your voice travel farther. An antenna shapes and directs the radio signal. Now, engineers visualize this focus using something called a radiation pattern. The easiest way to think of it is as a sort of topographical map that shows the antenna's signal strength in all directions. It tells you exactly where that antenna is designed to send and receive signals most effectively.
And if we look closer at that map, you can see a few key areas. The main lobe, that's the big one. That is the primary direction where the antenna is pushing its strongest signal. The smaller side lobes are kind of like weaker bursts of signal that leak out in other directions. And then you have the nulls, which are the gaps in between where there's little to no signal. So really, good antenna design is all about shaping these lobes to point the energy exactly where you want it to go.
And this brings up a really crucial distinction. Passive gain, which comes from an antenna, versus active gain, which comes from an amplifier. An antenna, like a megaphone, it just focuses the energy that's already there. An amplifier, on the other hand, is like giving someone a stronger voice. It actively adds new electrical energy into the system to boost the signal's overall power. Two very different things.
So, we've covered how radio waves are born, how we describe them, how they travel and interact with the world, and how we harness them. The next time you lose a Wi-Fi bar walking into another room, or your car radio fades out when you go under a bridge, you'll know exactly what's happening. So now that you know the rules of this invisible world, what do you notice about the signals that are all around you every day?